Hello friends, good morning. In last class already we are discussed about electric dipole and then we are finded electric potential due to electric dipole. So now we want to start new concept, potential energy of an electric dipole placed in a uniform electric field. See, in electric dipole already we know its length is 2a. If suppose here one diagram we are representing, here field is capital E is present, that is uniform electric field. In that field we are placing one dipole having length 2a. Friends, in electric dipole already we are observing two equal and unlike charges minus q and plus q also. That dipole makes an angle theta with that given uniform electric field observing in the diagram. Here AB is dipole, okay, that is having length 2a. That dipole makes some angle theta with that uniform field. See here on the charges in the case of uniform electric field, force is developed. So from the given diagram we are observing two equal and opposite forces are acts on electric dipole in opposite directions. From that two equal and unlike forces couple is developed. Previously we know about the concept of couple. From that couple, we may find torque value also. So, how we can define a torque developed? Okay, on this electric dipole is by the concept of torque. We know torque is equal to force into perpendicular distance. See, friends, from this diagram, once we want to find out how to get that perpendicular distance. See here, this is the given diagram. ABC is we are observing as one right angle triangle. In that right angle triangle, if we are going for sine theta means sine theta value is equal to, this is opposite side, that is BC, and hypotenuse is AB. So sine theta is we are represented as BC by AB and sine theta is equal to BC. Here AB is nothing but length of the electric dipole, that is 2a. So finally we are finding BC is equal to 2a sine theta. That only acts as a perpendicular distance to any force we are observing in the given diagram. Here from the diagram, let this is force means here BC acts as a perpendicular distance. Here F is acts like this means here also the perpendicular distance is BC. So friends, torque is equal to, we have the fundamental formula force into perpendicular distance. See, tau is equal to, here we are represented F into BC, therefore tau is equal to, instead of F I am representing EQ. Why reason is, by electric field intensity we know one notation, E is equal to, we have one fundamental formula that is nothing but F by Q. From that one, F is equal to, we are representing as EQ. So totally tau value is equal to EQ into 2a sin theta. Then torque tau is equal to, we are represented as E into P into sin theta. So why we are representing this P means, that is here electric dipole moment. We know previously electric dipole moment is P is equal to Q into 2a. Therefore tau is we are represented as PE sin theta. Suppose dipole is rotating through an angle d theta in a given electric field, then work done is we want to find out. So in general, work done is equal to, we have force into displacement, but in rotatory motions, work done or small changes in work done dw is equal to, instead of force we are taken as torque and instead of displacement we are taken as angular displacement. So here we may represent as dw value is equal to tau into d theta, then dw is equal to, already we are finding tau value is P sin theta, that P sin theta into d theta. Okay friends, already we are finding dw value is equal to P sin theta into d theta. So for getting a complete work done in uniform electric field, just we are applying the integration. So if a given dipole is making angles or changes its angles from theta 1 to theta 2 means we may represent that one as W is equal to integral dW from theta 1 to theta 2 integral limits we are represented. So that is equivalent to, in previously we know dW is equal to PE sin theta, okay, d theta. So this is we are represented. So in next further step we are representing as W is equal to PE into integral sin theta 1, okay, sin theta d theta from integral limits theta 1 to theta 2. We know friends, here P is a constant value. So here sin theta d theta is able to integrate in between the limits theta 1 to theta 2. Already we have one fundamental formula. Integral sin theta d theta is minus cos theta. So therefore W is equal to, I am representing here, P into minus cos theta into theta 1 to theta 2. Now further I am taken common minus. Okay, W is equal to minus P into cos theta, theta 1 to theta 2 limits were applied. Here upper limit is theta 2 and lower limit is theta 1. By integral formulas, W is equal to minus P into first upper limit value, that is cos theta 2, minus lower limit value minus cos theta 1. So by multiplying with minus in further step, we may get W is equal to P into cos theta 1 minus cos theta 2. So friends, this work is actually stored as a potential energy. That potential energy I am represented with capital U. Therefore, the W is equal to U is equal to, we are able to represent like this as PE into cos theta 1 minus cos theta 2. So what is the work done or potential energy in case of dipole placed in uniform electric field? That is W is equal to U is equal to PE cos theta 1 minus cos theta 2. This is the main formula. Okay friends, now I want to discuss one small case. If dipole turns to opposite direction in a given electric field, let for that conditions theta in 1 is we are observing as 0 degrees and theta 2 is equal to 180 degrees. So in the above equation we are represented as W is equal to, we are getting as P into cos 0 degrees minus cos 180 degrees. So W is equal to, we can able to write here P into, instead of cos 0 degrees we are taken as 1, already here minus is present, so minus we are represented. Cos 180 value is, we know, that is minus 1. Here totally we are getting on summation 2. Therefore final work done or that potential energy is 2PE. This is the one of the small application or case we are discussed when a dipole is placed in a uniform electric field. Okay friends, now we are going to new concept, that is equipotential surfaces. This is very important concept. So before going to this concept, a live example once I want to show here. Let's consider this is one surface. Okay, on that surface just I am represented 2 points. One is capital A and another is capital B. If suppose at a point A electric potential is VA and at a point B electric potential is VB. If suppose VA value and VB value is becomes equal, that surface we are treated as equipotential surface. So for example, in any surface that has the same electric potential at any point or at every point, that only we are calling as equipotential surface. See, any surface that has the same electric potentials at every point is called equipotential surfaces. So here we are represented VA value is equal to VB. Therefore VA minus VB value is becomes how much? 0. Therefore on equipotential surfaces the difference between potentials is becomes 0. So the potential difference between any 2 points on equipotential surface is 100% becomes 0. So friends, for this equipotential surfaces, a few properties we want to revise. What are the first and important property in equipotential surfaces? Means, for example, if you are moving a charge on equipotential surface, then work done is becomes 0. So how we are getting this work done is 0? For example, say work done in the moving charge on an equipotential surface we want to find. So by the concept of potential, we know potential is equal to work done on charge. So here potential Va minus Vb is equal to, I am represented as W by Q. So here Va minus Vb is equal to, already previously we are represented, that is 0. Therefore 0 is equal to W by Q. Therefore W is becomes 0. So we are concluding here one point. Work done is moving a charge over an equipotential surface is 0. Hello friends, one more important point. In equipotential surfaces, always electric fields is acting perpendicular to that surface only. So for example, clearly we can observe here, let this is one equipotential surface. So here electric field is we are observing as perpendicular to that surface. So we may conclude friends, the electric field is always perpendicular to the equipotential surface. So one more point we want to discuss. In case of equipotential surfaces, they never intersect each other. So why we are concluding equipotential surfaces are never intersect each other means, if both are intersects means at a same point different electric fields we may observe or different potentials we may observe at the same point, but it is not possible in case of equipotential surfaces. So no two equipotential surfaces intersect. So that is the one of the important point we have ready to discuss in case of equipotential surfaces. Okay friends, few points about equipotential surfaces we want to discuss. At any point on the equipotential surface, component of electric field parallel to the surface is 0. So previously we are represented one thing. Always electric field is perpendicular to equipotential surface. So here we are concluding parallel to equipotential surface electric field is becomes 0 only. That is one of the point we may conclude. So one more important point friends, if suppose equipotential surfaces are very close or very crowded to each other, then electric field intensity becomes a greater value. And if suppose equipotential surfaces are very less or very far distances, then electric field intensity becomes very less. So here indirectly we may conclude, okay, equipotential surfaces are crowded means maximum electric field intensity we may observe. Okay friends, now few cases we want to discuss here. Once observe carefully. In this case two diagrams I am represented. In first diagram, let's consider this is first equipotential surface and this one is another equipotential surfaces. Those two are placed parallel to each other. Here we are observing electric field intensity developed through those two planes. We are observing perpendicular to those planes only. So in the same way, for example, in case of point charges we are observed means, for example, here we are placed one point charge in these directions, in outward directions, maybe that field intensity will be acting like this. So in this direction electric field is developed, in this direction electric field, in this direction electric field, if it is a positive charge. In that condition we have chances to construct some concentric circles or concentric spheres we are observed. So here the equipotential surfaces are a family of concentric surfaces. So for example, if you are considered this this sphere, this is having same potential at all the points. This is we are calling as one equipotential surface. For example, this is another sphere we are considered means here value of that potential will be varies, but all these values on this surface remains constant, then this is also acts as another equipotential surface. Okay friends, now we want to discuss about new important relation, that is relation between electrostatic potential and electric field intensity. This is very important, and from this relation only we can able to solve so many problems in competitive examinations also. How we are getting that relation between electric potential and electric field intensity, now we will observe. Okay, this concept is able to explain with the help of only equipotential surfaces. Once observe friends, here in this diagram I am taking two equipotential surfaces. One is named as A and another one is named as B. So on this surface, equipotential surface A, potential is we are taken as V. On surface B, equipotential surface, we are taken as V minus dV. These two are separated by a distance dr. So for example, here one point we are chosen on the surface B. Now we are observing the perpendicular distance from P to surface A is we are taken as dr. For example, when a unit positive charge Q, let that Q value is equal to 1 is taking towards surface A. So in that condition, actually electric field intensity will be acting in this direction, and this one is we are bringing from B surface to A surface against to this electric field. By observing the diagram, E bar and D bar is acting in opposite directions only. So now I am mentioning here, taking towards A from B to A against the electric field E bar. Then we want to discuss about work done. By the concept of work done, we know dW value is equal to here F bar dot dr bar. So dW is equal to, now I am representing here E bar Q into dr bar. Okay, so since we know by electric field intensity E bar is equal to F bar by Q. So here we are choosing already Q is equal to 1, that is a unit positive charge. Therefore dW value is becomes as E bar dot dr bar. dW is equal to E bar dot dr bar. So therefore dW is equal to, we are representing E into dr cos 180 degrees by scalar product concept. What is the thing here? dW is equal to E into dr cos 180 degrees. So dW value is equal to, we are taken as minus E into dr, since we know the thing is cos 180 degrees value is equal to minus 1. So friends, just we are representing the thing dW is equal to minus E into dr. Let I am taking that one as equation 1. Once remembering the electric potential concept, by electric potential concept we know dW value is equal to VA minus VB into Q. So here dW is equal to, already we have on surface A potential is V, and on potential surface, equipotential surface B, potential is V minus dV. Already we are taking Q value is equal to 1. On simplification we are getting dW is equal to dV. So that is we are chosen as equation 2. So friends, already we are getting the two equations, dW value and dW value in equation 1 and 2. On equating those two equations, we are getting as minus E into dr value is equal to dV. Therefore E is equal to, we are represented as minus dV by dr. This is the concept we are represented. So final relation in between electric field intensity and electric potential is E is equal to minus dV divided by dr. Thank you friends.